Perfect. And our recording has started. Thank you, guys.
Cool. Thank you. So is it going to advance?
I would just click it to the next one. There we go.
Probably. If you want to say hi to the kitty cat, if you want to play.
What was that? Sorry, can you repeat that? All right, we are going to get started. Here's Phil.
Hi, guys. I'm Phil Emory with Enclosure Engineers. A few months ago, it might have been almost a year ago, I got a call from McKinstry, and I understand there's someone from McKinstry who's on the line. And they had an issue that they wanted to discuss, and I took it as an opportunity to not only discuss that issue, but several things. And an opportunity to talk several things that have been happening in my world when it comes to building enclosure testing and the tightness of the building. After that meeting, which I felt was really productive on my end for the stuff that I wanted to be able to get across to them, I thought I'd be able to reach out to the ASHRAE folks here locally and see if there was any interest, and there was. So it's kind of a rehash of the conversation that I had with McKinstry, plus a few new items that have popped up in the last couple months. And it's going to be several different issues, but it all kind of ties together. And if you're just kind of patient with me as I work through this, I think you'll understand exactly where I'm coming from. So currently, I'm the NEBB chair for building enclosure testing. And I also teach the certification program for the building enclosure testing for NEBB. I have served on the ABBA's BET committee, which wrote their standards for doing a building enclosure testing. And then I went and took their field auditor exam and passed that. And I've also got a level 2 in thermography. And I'm currently working for NEBB Engineers. So back a bunch of years ago, the United States enacted a policy that they wanted to start saving energy in these buildings. And I'm sure all of you are aware of this and where it all started and where it came from. And then shortly after that, the Corps of Engineers got involved with it, with the building science guys, and they really wanted to start trying to bring it, get the efficiencies there that they really were looking for. And a lot of architects were going along, and they were doing new things with insulation and building wall types, but they really couldn't get it there. And so the building science guys looked at it and they says, well, why don't we take a look at adopting what's been going over in Europe for quite a while and actually start fixing the leaks that are in these buildings rather than just using different materials. And they did that. And so they formed up a group with the Air Barrier Association of America, and a bunch of them started working on a new test protocol for doing the air leakage requirements, and it got placed in the U.S. Army Corps of Engineers air leakage test protocol for building envelopes. They adopted ASTM E779, which is the standard method for determining air leakage by fan pressurization, and they pulled a target figure just kind of out of their back pocket, and they set the leakage rate of 0.25 CFM per square foot at a pressure of 0.3 inches. And the first year that they were doing this, which was about 10 years ago, no one across the United States was passing this. And it took them at least a year to 2 years to where some of the contractors started getting below this number. And then once they did get below that number, all of a sudden they really started dropping fast. So along comes Washington State and the City of Seattle back in 2012. And Washington State and the City of Seattle really are one of the first municipalities or groups of municipalities that have adopted what the Corps of Engineers was trying to do. But they set the leakage rate at 0.4 CFM. But basically, they took exactly what the Corps of Engineers standard, their protocol, and they adopted it and brought it into the Washington State and the City of Seattle code. But they just changed the leakage rate from 0.4 down to 0.3 inches. And then currently, both have allowances, both meaning the Washington State and the City of Seattle have allowances. If the building fails, we can still work out a deal where they can get their certificate of occupancy and everybody's happy and off we go. In 2015, just recently, a few months ago, the City of Seattle amended their leakage rate from 0.4 down to 0.3 inches. Same pressure that we're testing at. Washington State, in the upcoming 2018 Energy Code, is going to amend it from down to 0.4 down to 0.25, down to the Corps standard. And they're going to require that all buildings now pass. Okay, so we should start seeing buildings become significantly tighter, and getting these things to pass become more of an effort, time consuming in the construction schedule. So real quick, there's a couple standards out there. There's the testing standards, which is 8779, and that's the one that most people see when it comes to air leakage testing. There's ASTM 1827, which I use significantly quite a bit out there, and it's just an adopted version of 779. Corps of Engineers wrote a protocol that basically uses 779, and NEBB, their procedural standard, we have basically exactly what the Corps of Engineers has for 779, and then we included 1827 into our protocol too. Both methods work, they're both great. They both do exactly the same thing, just a different method in which you'd get there. ASTM stands for prime leakage method. This method measures leakage throughout the building. And the way it reads right now, the stuff that I have there in red, therefore strong winds and large indoor-outdoor temperature difference shall be avoided. And what's a strong wind and what's a large indoor-outdoor temperature differential? No one knew. And there were all these different weather protocols that were forcing you to where really you should be using this method to do the test. So that's when the Corps of Engineers sat down with ABBA, and they really tried to figure out a way to test large buildings and get rid of the weather restrictions. And they did that. And how did they do it? They modified a few different things. They modified the baseline readings, which is just you testing the building with everything all closed up, buttoned up, and what's the differential pressure across the building. And that's your baseline reading, and if we bump those up and increase the amount of time that we do them, we get a more stable reading. They modified the induced pressures that they're putting in there. They added induced pressures, and they required testing in both directions. And that made the test much more repeatable, and they were able to do it in a little bit more adverse weather conditions. NEBB came along. We were asked to form a certification program by the Army, Navy, and Air Force, which we did several years ago. So we didn't try to reinvent the wheel. We just took what the Corps of Engineers had developed and took it a little bit further. And we also added 1827 in there. When we test, we can test the building when the air barrier is complete, no further penetrations will be made. A lot of people right now are waiting till the very last minute of a project and getting the test done. And so if there were any repairs or anything that they needed to do to the air barrier, there really wasn't anything they could do about it. Well, in today's world, we don't have to pass the test, so we just kind of write a letter saying where we're at and where we're at and what's going on. But in tomorrow's world, they're not going to be able to get away with this. And so they've got to start thinking about when to do this test in the scheme of the building construction. When you test, you want to test under the most stable environmental conditions possible. You want really low winds, you want steady temperature, you'd like to have no rain or snow, and you'd like to get it done early in the morning so the solar load doesn't have the time to start affecting your stack effect or anything else on the building. And you want to test in the shortest time frame possible. So I do a lot of my testing early in the morning. Takes 3 to 4 hours for me to run a normal test and get out of everybody's hair and off I go. When we report testing, we report the testing at 0.3 inches, the amount of leakage at 0.3 inches is 75 pascals. But, and I've talked to a lot of engineers about this, and I says, what good is it to an engineer to hear what the leakage is at 0.3 inches? Wouldn't you rather want to know what the pressure, what the leakage is at some operating pressure that you anticipate the building to operate at? And every now and then I get a yes. And so it's very easy for me to just simply, I don't have to retest the building. I just go back to my computer, I put in a new reference pressure, and bam, I spit out where the leakage is for that, at that pressure, whatever pressure they want the building at. Understanding that the leakage may be different, where it's leaking and how it's leaking may be different at different pressures. And that's kind of what the McKinstry guys were starting to experience. Building enclosure testing in the nucleus, I have a sample of 28 projects, and it's just the last 28 projects that I've done in this year. These are commercial projects. None of them are Corps of Engineer projects. These are all just commercial in Washington State, City of Seattle. The average enclosure, all 6 sides of the building, the enclosure I'm testing is about 41,000 and some odd plus feet. That's a little small, but usually most buildings are 80 to, 80,000 and up. Of the 28 projects so far this year, only 61% of them have passed the leakage rate of 0.3 CFM per square foot. That's not a very good passing rate. Of those that failed, the leakage rate average was 0.65 CFM. So we're way above the 0.4. If we drop it down to 0.25, only 21% of the buildings currently being constructed are going to pass. And they're not going to get their certificate of occupancy. Here's a graph of those 28 projects. You'll see that across the bottom there is the square footage of the envelope. And then on the horizontal is the leakage rate at 0.3 inches. And you can see where 0.4 line is, and that the smaller the building, the more the buildings are failing. The reason buildings fail, and where they usually fail, is at their major transitions. Their floor-to-wall joint and their roof-to-wall joint are usually the places where they fail. So if you think of a building being incredibly tall, several stories, the percentage of those transitions is significantly reduced versus a shorter building that has the same footprint. So what was happening with McKinstry is that they were looking at a building, and inside the building there was a fire-rated shaft. And the fire alarm calls for pressurization, so they were inducing a pressure into the shaft. The shaft was then leaking to the rest of the interior side of the building. The leakage that was coming out of the shaft into the building would leak from floor to floor, and then some of it would actually exfiltrate out the building. But as the buildings get these air barriers installed and they become tighter and tighter, the building's going to start seeing some back pressure. So the air that you were moving out of these shafts in the past, you may not be able to move out of the shaft with the same amount of fan in the future because the building's going to start putting some back pressure on you. So what do you do with the air? Currently, the way the code reads, and this is what I've asked a lot of the mechanical design firms is to help me out here and start pushing on the architects. Also, I do the same thing with commissioning people. Because the code reads that they're supposed to identify this air barrier on the drawings. And a lot of companies out there create a set of air barrier drawings, plan view, elevation view, and all these details. And this is a code requirement. But rarely do I come across any jobs lately where I'm bidding, and do I see any type of drawings that show these drawings or stating it where the air barrier is. I have no idea what portion of the building the air barrier is located or where it's located and what it's doing. You guys, the mechanical design firms out there, are trying to base your design off of this air barrier system. In the past, you've had a model where you've thought, okay, is the building going to be tight, average, or leaky? But recently, those models have greatly expanded based on the type of air barrier materials that are supposed to be used, that people are using out there. You should be getting from the architect in your design phase what that air barrier is going to be and where it's going to be located, because that's going to drive your design. And what I've been asking the mechanical or the engineering firms to start pushing on these architects to start developing these drawings, get them developed before we go in for permitting. I've also talked to a lot of municipalities, and they say, and I ask them, I says, why are you guys approving these drawings if there are no air barrier drawings in them? Whenever I do design review, I go through the construction documents and I try to figure out where the air barrier is, all 6 sides of the building. I look at its components, the continuity of it. There should be no gaps in it. You shouldn't ever lift up your pen if you're drawing or going through this air barrier. The materials should have a leakage rate of 0.004 CFM per square foot at 75 pascals. The assembly, which is just where 2 air barriers match up, should be 0.04 CFM at 75 pascals. And then the enclosure is at 0.4 CFM, or in the case of the Washington State Energy Code, here in the next energy cycle, it's going to drop down to 0.25. To the right there is a standard wall, and you'll see that somewhere in that wall, there's this thing called an air and vapor barrier. And it's providing the air barrier, but we want to see its continuity as it wraps up into the ceiling system or wraps into the floor system. But it's got to be there. We've got to easily be able to find it and see it. The picture that you're seeing on this slide shows the air barrier, which is the plastic material at the top of the roof line, and they've just stapled and taped it to the roof system and wrapped it into the walls. And it's not going to be a sturdy system. It's not going to hold up. It's going to leak terribly. It's not a good air barrier that you're seeing there. This one shows a TAC system, which is a really good air barrier product, coming up the exterior side of the building, wrapping around, and it does a great job of wrapping into the ice system of the roofing system. When the Corps of Engineer project started doing this type of air barrier transition from the wall into the roofing systems is when we really saw a lot of the numbers and the tightness of the buildings coming down dramatically. But this is the kind of detail that we should be able to see in the architect's drawings. The series of photos show some really poor and some really good air barrier wraps around penetrations that get stuck in these walls. Here's a plan view that an architect has done for a Corps of Engineer project, which shows me where the air barrier is located. It's the dash line. It's not the entire portion of the building, and they've also got a calculation for the square foot. If I saw this drawing going through everything I'm doing, I'm good to go. I'm good to test. I know exactly what portion of the building I'm testing. I know exactly where the air barrier is, and I know exactly what the quantity of the air barrier surface is. So I'm going to be testing that air portion of the building that's in the red right now, and everything to the right of it is not included. So we're going to bring that to atmosphere. Here's a project that has multi-zones, several pods and a UEPH. The intermediate wall between each of these pods is not an air barrier wall, but we're going to be testing these pods in sections. One of the cool things about the air barrier requirements, especially for the Corps of Engineers, is they require that the air barrier testing also determine where the leakage is occurring in the building and how it's leaking. And they require thermal imaging to be the means in which we try to find the leakage in these buildings. Thermal imaging is a incredibly good tool for doing this. It shows great documentation. You're able to see it from a distance. You're able to document it. If the thermal imager is not very qualified, he or she can make some pretty bad mistakes when it comes to it. All you need is a good temperature differential between the surfaces that you're taking the images from, 10 degrees outside versus, a differential to the 10 degrees inside. But you'll see here the bottom one shows where there is some leakage. Those blue points up there, the ones that are very dark and blue, are showing where the leakage is coming through the flutes up there in the ceiling system. In this photo, I've just expanded that, but boy, you can go exactly up to those spots. Try to fit. Here's the way the mitigation is taken care of. They've stuffed those flutes with foam, and then they're coming back with a nice fluid applied product that does spray in there, and then they'll come back with it and go about 4 inches to either side of it with that same orange spray. But they're creating a very tight envelope in doing so. Sometimes, this is supposed to fly in, so it kind of ruins my story here. But sometimes the problem isn't us. And when I say us, what I mean is the control people, the balancers, the mechanical engineers. Just recently, we were on a project. Neudorf Engineers was the balancing contractors, and Siemens was actually the control contractor. And they had a room that was supposed to be negative, and it was. And the room temperature set point was 70 degrees Fahrenheit. The actual room temperature was 80 degrees. The thermostat on the wall was thinking that the room was 68, and the control contractor Neudorfer and TAC and the control contractor Siemens and the TAC contractor Neudorfer were standing in the middle of the room, pointing their fingers at each other, wondering why in the hell the room wasn't controlling right. And the answer was very simple. And to the right there, you'll see a picture, a thermal imaging picture that explains exactly what was happening. The room was negative. The thermostat was located on a wall, which cold air was being pulled into the room. Cold air was rushing by the thermostat, and the thermostat was seeing 68-degree cold air coming racing across it. So, of course, it was trying to heat the room. This sort of thing we're starting to see more and more as buildings start getting tighter and tighter. The building science people that I've been talking about have been focusing on the exterior portion of the building and nothing on the interior portion of the building. They're doing a great job in creating this envelope that's bringing the building tighter and tighter. And we're going to see some buildings get tighter and tighter. I've seen buildings down at Joint Base Lewis McChord that are around 0.06 to 0.08 CFM per square foot of leakage at 0.3 inches. But why they reported a 0.3, I don't know. But that's what they've decided. And actually, the reason why they did pick 0.3 was to get it off the baselines, because they figured that they tested buildings at a significantly high pressure, that they could be more repeatable, and especially if they tested in both directions. But it really doesn't do the mechanical engineers any help or design help in establishing how much leakage you're going to see in a building. But again, they're focused on the exterior walls of the building. They don't focus so much on the interior walls. Neudorfer has done quite a bit of work at some BL3 labs across the United States. And in the hospitals, which we've all done in and around here in Seattle. And we all know that there needs to be a pressure gradient established throughout these buildings. If the building enclosure people or the architects would start taking some of the same thinking that they use now, or that they should be doing on the exterior side of these buildings, then we could bring that same technology onto the interior side of these walls and start building rooms where the pressure gradients are much easier to control to. Mechanical systems would get smaller. We wouldn't have to punch so much air. We'd still get the air change per hour, but we'd be doing the same thing with the environment on a microenvironment on the inside of these buildings that they can on the exterior side of the buildings. And I've gotten very few architects to even start thinking about that. There's a few general contractors who understand what I'm trying to do with the architects, but basically, if the architect doesn't draw it, they don't do it, they're certainly not going to build it. One of the the stories I always tell people is everybody starts complaining about the cost of all of this and how much is it costing. A bunch of years ago, when I was down at Joint Base Lewis McChord, it was the general contractors were doing these projects, and they were all design build projects. And I asked one of the general contractors, I says, what's all this costing you when it comes to the design, the products, and me coming out and testing? Because it's not cheap. And they were at 0.1% to 0.2, or 1% to 2% of the whole building cost. That was substantial, but it wasn't too much. And I thought, okay, that's okay. But then all of a sudden, these guys started passing, and it seemed like they were doing so much better. And I ran into that same project manager and some other guys from his firm, and I asked them, I said, remember the question I asked you a couple of years ago about how much this is costing you? And they said, yeah. And I said, where are you guys at now? And he says, oh, we've gone from the 1% to 2% that I told you before. We're well below 1% now. And one of the other project managers said, nah, we're down to 0. And I said, well, why do you think 0? The reason was because they focused on this air barrier, when to do it, getting products in a little bit sooner than they did normally, for instance, the windows and the exterior doors and some of the other hardware, not doing any trade stacking. They were turning these buildings over 4 months earlier than they did on the same type of building several years earlier. And so they figured that on the overhead that they were saving, they were really getting out of there that much quicker, and they were saving the money, and it was driving all this cost down to 0. So it really isn't a big financial thing if we can just get the general contractors and the architects to really start focus on what they should be doing. If we could get these drawings to have these air barrier systems, and for you guys to understand how much leakage is really going to be occurring in these buildings before you start your mechanical design, we'll understand what we need to do because of this air barrier or intermediate air barriers that are established throughout the building. But we could get these drawings approved and out on the street with all the information that's really needed, rather than people scrambling at the last minute to try to get this test done and performed. As I said earlier, basically we're being called in at the very end of a project. You guys have already done your fire alarm testing, the balancing's done, the commissioning's done, and I'm in there trying to do this pressurization test, and it's failing. I'm telling the general contractor where the building's failing. He simply acknowledges those failures, writes it up in a letter saying, hey, it's too late, we can't do anything about it, we can't get to it now, this building's being turned over tomorrow. He takes that letter and my report, and it sends it off to the inspector, and they're fine. They've got their report, they've got their test, and they're good to go. But the next energy cycle, when Washington State drops it down to the 0.25, and the requirement of passing for C of O is there, the thing that I've been asking, I would say, okay, what's going to be in the teeth if the building fails? And the answer I've been getting back is, well, they're not going to get their C of O. And I'm just going, oh, I don't want to be involved in that lawsuit, and I don't want to. It's got to stop. We've got to push the architects now to really get on board and start doing the testing or the proper design. Whenever I go off and I talk to the architects and I discuss with them, and one of the first things I ask them, I says, when it comes to barriers, be it vapor, water, air, whatever type of barrier, do they do the design themselves, or do they sub it out to somebody like B or RDH or Morrison Hershfield or some of the others that are here in Seattle? Or do they do that design themselves? And if they hesitate in answering that question, I know I've got a problem. And they don't. And they don't put it in their designs. It's not in there now when it's been required since 2012. And there's a train wreck coming. And one of the things that when McKinstry called up and they wanted to talk to me about this pressurization that they were seeing across the building, is I was hoping to get across to them also was, guys, we need to start doing a review before it goes to permitting and request these drawings, because the drawings are supposed to be there, and we're supposed to be designing the mechanical systems off of these drawings based on the type of materials and where the stuff is located. It's not all, like I said, it's not always the entire building, and it's not always at the exterior perimeter. And it's driving a lot of contractors nuts in trying to get these buildings to pass. So that was why I asked, and thanks for letting me take a few minutes today. I know I didn't take up all the time that you guys had slated, but that was one of the things that I really wanted to get out in front of everybody. They can always contact me at Neudorf if you guys have any questions or want me to go somewhere and talk to somebody or anything that I can do to help you guys, or if you want to talk about this more, I go anywhere, anytime. But thank you for your time. Thanks for letting me come in today, and that's all I had.
Awesome. So before we open up for questions, I just wanted to say thanks again to those ASHRAE sponsors that didn't make it onto the recording. We have Mechanical Sales, Train, McDonald Miller, Johnson Barrow, PAE, McKinstry, Proctor Sales, ATS Automation, Rushing, Cezanne Group, Columbia Hydraulics, and Viega. So if you guys have any questions online, please feel free to unmute yourself, and we will be taking those now.
This is Rick with Knauf Insulation. Question I have is, when you spoke, one of the slides, you spoke to the building officials and asked them why they are approving plans without air barrier, thermal boundary conditions clearly indicated on the drawings. What was their answer?
Because they don't know what it is they're supposed to be looking for. They're not educated on what a set of air barrier drawings look like or what they should be including. And it's the code, but they don't know what it is, really what they're supposed to be looking for.
Well, that's a shame, I should say, but I'm not surprised.
Yeah, they've got a difficult job, and to try to keep up with everything is quite difficult. But boy, there are companies out there like some of the ones that I mentioned, especially B out there. They do a phenomenal job with drawings. And it's not one or two drawings. It's an entire packet, and they've got them labeled as the BE envelope drawings. And if you could get those in front of the code officials, that's one of the things that through the NEEC guys here that we're holding the seminar out of, they've asked me to come in a few times, and they've brought in some code officials, and so we're able to start getting to them. But boy, again, as a team going forward, trying to get the code officials on board and realize and understand what it is that what we're all talking about is a huge task, but it needs to be addressed, and we just need to keep pushing it.
Yeah, I agree. I do have another question. You spoke about the building science community not pushing for interior air barriers, internal air barriers, as well as the exterior air barriers. I've been working in the field for a number of years, and I've always myself have promoted interior air barriers, obviously where they're needed. What's it going to take to get the building science community to start understanding that the interior air barrier and its locations are as important as the exterior air barriers?
Right. So a bunch of years ago, when I was working on the ABBA committee, they were doing a presentation down at ASTM down in Atlanta, Georgia, and they asked me to come down and do a presentation on ASTM 1827. And during the presentation, a couple guys in the audience started arguing. So I just kind of stepped back and listened to it because I didn't know what the heck they were doing. And all of a sudden, the head guy from ASTM there came up and took the podium away from me and he said, guys, he says, we've been through this a million times. We tried to sell this air barrier and through the building science guys, we tried to sell it in the building code. But no one can come out and say, if you put in this air barrier, we're going to increase the life of your building by X amount of years because the built bricks and all this other stuff aren't going to start falling off the side of the building. Your building is going to, the strength of it, the integrity of it is going to last a whole lot longer, which is true. But they were able to sell it, this idea, this concept, into the energy code. Because we do save about 30% energy in these buildings, at least 30%, if a proper air barrier is installed in these buildings. So they've been talking back and forth, the building science guys and people like the Corps of Engineers, without really getting ASHRAE involved in this thing, in this conversation. And ASHRAE has kind of sat off to the side and said, well, we'll take the benefit of you guys making the building tighter, but it's not. And so when I've worked with ABBA, I've asked them and pleaded with them to think a step further and let's start bringing it into the inside of the building, because they do have a strong push on architects and other people in the science of air barriers. But again, when I was doing a job here in Seattle and was trying to push the architect to think in those lines, it was, what do you mean talking? What do you mean we're going to take this intensive care unit and create an air barrier inside this intensive care unit? And I said, well, you're going to take the same science that you did for these exterior walls, and we're just going to bring it in. We're going to fill holes in this wall. And in an intensive care unit, you've got holes in walls everywhere. You've got conduit penetrations that need to get filled. You've got duct work. You've got all sorts of different penetrations. And to get the architect and the general contractor to take that science that they did on the exterior walls and bring it to the interior walls it's just a learning process. So again, I think, you've got the science is there. Why not just focus a little bit on bringing it into the interior walls so that we can make these rooms a little bit airtighter? And at this hospital, the children's one, they were very, very successful in being able to fill some of these leaks to where they could get the control system to do what it was designed to do. It was incredible.
Yeah.
But again, it's just education.
Yeah. Appreciate that. One more just quick question is the presentation going to be recorded and sent out or not?
Yes, it is currently being recorded. If there are no technical difficulties in getting that off the computer and all that fun stuff, then yes, it will be posted on the ASHRAE website in conjunction with this event.
Thank you.
Yeah, and I guess the last thing is I sure could use ASHRAE's help in promoting the idea of many environments within a building.
Hey, this is Skander Spies with McKinstry. Thanks so much for recapping this again. I was at your original presentation at our office. One of the questions I wanted to clarify, especially when we've got an insulator on the line from NOF, I feel like often it's there's a gap in air barrier installations between, is the architect drawing a really constructible detail? Because a lot of good air barriers come down to, can they be constructed? And then, if my job as the mechanical engineer is to kind of reinforce the notion of needing this air barrier in these envelope drawings, I think there's another piece where the general contractors really have to get involved, and also probably installation subcontractors get involved, depending on who is actually responsible for installing that air barrier and doing some amount of detail review when the building is still in design. I didn't know if you could speak to kind of how we can drive that process better.
Absolutely, that's a good point. Because often when it comes to the air barrier, a lot of people just think of it, okay, it's that thing inside a wall, but it's really not. It's the thing that wraps all 6 sides of your building. So it could be a contract slab as it comes up. How does it continue into the walls? As it comes up the exterior side of the walls, how does it wrap into the roofing system? And when you're talking about doing all of that, you're usually talking about multi-trades and how they're involved. The compatibility of these materials. You can't just bring one type of material up a wall and then another material up from the roof and try to get them to seal together and expect it to work. A lot of them just aren't compatible. So having an expert along those lines that really can take a look at the air barrier system as a whole, not just as where it is in the wall systems or anywhere else, but as a whole, be able to look at it and be able to say, yes, this has got continuity throughout the building and it looks very good, is very, very important, especially with a lot of these materials. The materials are changing dramatically today's world. It wasn't too long ago where we saw very, very few fluid applied products. Mostly all of them were some sort of paper product. The fluid applied products became more and more prominent out there, and we're seeing a lot more buildings being installed with a fluid applied product. But you've got weather conditions out there that you have to be concerned about, the humidity and so many other things that I know a lot of guys that they say, no, I'm going to stay with a paper product because I can install that thing anytime, anywhere. So you're absolutely right, where it's not just the general contractor's issue. It's the design firm. He's got to be able to design it. It's got to be able to be buildable. People like ABBA and, again, some of these guys that have specialized in this, like Morse and Hertzfields and the RDHs and B's and a few others here in Seattle, can really help them out in providing something that is designed correctly and is buildable. A lot of the general contractors that have been through this, especially the ones that care about it and really have focused on it, that have done some well. And there are quite a few here in the Seattle area that I've worked with that are really focusing on doing a good job when it comes to getting this thing installed right. And they understand it a little bit better. But it's a lot of general contractors that need to be brought up to speed on that. And it's their subcontractors. You've got all sorts of different contractors, again, the multiple contractors that have got to understand it, that this thing needs to be continuous. You really are filling in the holes. You can't have these holes. You can't do it the way you used to do it. You've got to caulk here or you've got to put some caulk there. And again, for them, it's just an education process. But once they learn it, it is very simple, but it's a learning process for all people. It's the sub, the general contractor, the architect, and everybody else involved.
This is Rick with Knauf Installation again. Thanks for that. That was a great question and a great response as well. One of the things that I've learned over the many years I've been in the industry is that if you give the responsibility to the trade contractor who creates either a transition or a hole or a penetration or some potential air leak, they're responsible for that, the transition, the hole, the cutout, whatever it is, they're responsible to make sure that those are sealed correctly. Otherwise, their particular job is not done. So, and I'm agreeing with you with the coordination from the general contractor and the trade contractors. That conversation has to be made very clear. Assuming that the architects have done the air barrier drawings correctly, then the contractor needs to sit down with the trade contractors. Basically, if you drill it, you fill it. If you put a counter flash over a flashing, you've got to make sure that particular transition, whatever it is, roof to wall, wall to window, any other fenestration, penetrations, what have you, that's the responsibility should be the responsibility of the trade contractor who's doing that particular detailed install. And that way you can have good QA right on site. When these guys say that they're done, you can review everything, and you might even be able to do some small testing in isolated areas as well. But that's, my opinion over the years has been that if you drill it, you fill it. So that's just a comment.
Yeah, absolutely. The Corps of Engineers and NEBB, in their standards, their protocols, part of the things that both of them require is that there be a pre-con meeting for the air barriers, and that all the subs, general contractor, architect, everybody involved should attend a pre-construction meeting to not eliminate, but try to reduce those issues exactly that you're talking about. If someone's bringing something up a wall, and he's going to be the first one there. If he's got this material, okay, are you going to leave 6 inches of material at the top of it that the roofing guy can then grab a hold of and then seal to, or is the roofing guy going to overlap, bring the material down, and they're able to discuss which subcontractor is going to be there first, which one second, which one third, and to button the thing up. And those meetings are very, very productive. When they don't have them, they're shooting themselves in the foot quite a bit.
Yeah, and this Skander again, to chime in on that, I wonder if maybe even better than a meeting, some well-placed notes, because I don't think many of the trade installers are necessarily looking at the drawings from the standpoint of the air barrier, but if we, as the mechanical engineers, or whoever, if I put a piping penetration through a roof or through part of the air barrier, I'm probably way more likely to know that I just put that pipe through the air barrier. So calling it out in a note, either general note or keynote or something, to highlight the fact that they would need to seal it feels like a good idea.
Yeah, absolutely. It's just like the fire stopping. It's almost identical, the issues that you've got there.
Awesome. Well, if we don't have any other questions, I would like to close this up. Again, my name is Bailey D. Phelps, and I am the chairman of the TAC committee. If you have any ideas of seminars or tours or interesting things going on in our industry, feel free to reach out to me at TAC, T-A-C, at PugetSoundASHRAE.org, and I'd love to organize another one of these with your topic. So anyways, I appreciate your guys' time and look forward to the next time we meet up. Have a great day.
Thanks.